See, haloarenes are not easily undergoes nucleophilic substitution like haloalkanes. Haloalkanes easily undergo nucleophilic substitution reaction in normal conditions, but haloarenes are not easily undergoing nucleophilic substitution reaction. If they undergo, that is at the drastic conditions. So haloarenes are less reactive towards nucleophilic substitution reaction as compared to haloalkanes. So what are the reasons? There are three basic reasons. Number one, partial double bond character of CX bond. Number two, difference in hybridization of CX of C of CX. Number three, polarity of CX bond. So there are the three reasons that why haloarenes are less reactive towards nucleophilic substitution reaction as compared to haloalkanes. First one, you see partial double bond character of CX bond in haloarene. If we consider haloarene, see X, already we have discussed. Now because the hydrogen atom here in conjugation with this pi system, what happens? It undergo resonance. So this comes here, this comes here. So we will get what? We get what? Carbon X minus. Okay. Now again this will undergo resonance. Think about it. Carbon X plus again we get what? Carbon X plus. So here you see this haloarene halogen atom present to the benzene ring undergo resonance. And again this will go come and this comes, this will get what? X. Okay. That will say the halogen atom undergo resonance and there is a double bond created between the X halogen and the carbon. You will see double bond between C and X, double bond between C and X, double bond between C and X. Now because of the partial double bond character is arising between C and X, the CX bond length decreases. Because the CX bond length will be less in double bond as compared to the single bond. So here, due to formation of C double bond X, the CX bond length decreases. That means the CX bond strength increases. Bond length decreases, that means the bond strength increases. Because the bond strength increases, the CX bond cannot break easily. That means the CX bond is not very much reactive. So this is the reason why the haloarenes are less reactive towards the nucleophilic substitution reaction. Unless the CX bond breaks, the X halogen atom will not be replaced by another nucleophile. That means the reactivity of the CX here decreases due to what? Partial double bond character development. Number one. Number two, difference in hybridization of C in CX. This carbon is what your sp2 hybridized. sp2 hybridized. But in haloalkane, this is what your sp3 hybridized. Okay. Now because of sp2 hybridization in this carbon, the S character is more, and more the S character, more the electronegativity. Due to increase in S character, the electronegative nature of the carbon becomes more. That means because the electronegativity of this carbon atom is becoming more here, the electronegative difference between the CX becomes less, and this decrease in electronegative difference decreases the polarity, and because the polarity is decreasing, the reactivity of the CX bond is decreasing. That's why the CX bond in haloarene is not so much reactive towards nucleophiles. Okay, so these are the three reasons why the haloarenes are not more reactive towards nucleophilic substitution reaction. Clear? Number one, partial Dalton character development within the C and X. Number two, difference of hybridization of the C, like the haloarene is sp2, haloarene sp3, and due to this again the polarity of the CX bond decreases. Okay. However, if you give drastic conditions, the haloarenes may undergo some nucleophilic substitution reactions. Like the halogen atom can be replaced by the OH group, you can get phenol. The halogen atom can be replaced by cyanide groups, Cn minus, you can get cyanobenzenes. Okay, now so can be replaced by the ammonia group and you can get the aniline. Okay, number one, replacement by OH minus, formation of phenol. This is called what? Dawes process. Dawes process. You can say. Okay. Simply we can take chlorobenzene, okay, plus NaOH, 623 Kelvin, 300 atmosphere pressure. Okay, we get ONA, then your acidic hydrolysis, you get what? The phenol. This is what? Phenol. This is what? Sodium phenoxide. This is what? Chlorobenzene. So chlorobenzene undergo nucleophilic substitution reactions, okay, to give out phenol. Chlorobenzene maintained with your NaOH at 623 Kelvin with the 300 atmosphere pressure. Then we are getting sodium phenoxide. This on acidic hydrolysis giving your phenol. But in the contrary, if we compare, if I take your Ca3Cl plus KOH aqueous, simply Ca3Cl aqueous KOH, I will get what? Ca3OH. So in haloalkane, the chlorine atom is simply replaced by OH minus ion with the aqueous KOH. Whereas in haloarene, we have taken NaOH 623 Kelvin, 300 atmosphere pressure, then acidic condition, then we are getting phenol. This is the example of how the haloarenes are less reactive towards the nucleophilic substitution reactions. Okay. here. Replacement by Cl minus. See, if I take chlorobenzene Cl, okay, plus CuCl (473 Kelvin) cyanobenzene plus CuCl. This is called your benzonitrile or cyanobenzene, or you can say phenyl cyanide. Okay, so chlorobenzene, okay, CuCl 470 Kelvin, what your cyanobenzene. Number 3, replacement by ammonia. Now already I have told you that haloarenes are less reactive towards nucleophilic substitution reactions because of the already we have discussed because of the 3 reasons, that the partial double bond character, less polarity, and hybridization. Now, however, the haloarenes can be reactive towards nucleophilic substitution reaction if electron withdrawing groups are present at ortho or para position. So when electron withdrawing groups are present at the ortho and para position, then the electron density on the benzene ring decreases. That weakens the CX bond, so that a nucleophile can easily replace at the hydrogen atom. This we can explain with the help of an example. If you take chlorobenzene NaOH, we are giving 623 Kelvin and 300 atmosphere pressure, then we are getting the phenol. That means the halogen atom is replaced by the OH. Now when in this species nitro group NO2 will be present at the ortho and para position, or para nitro chlorobenzene or ortho nitro, then the conditions will be different. With some less temperature, the species can undergo nucleophilic substitution reaction. If you place one NO2 group at para, it will require some less temperature. You attach another NO2 group, another nitro group, again the temperature will be less. And if you place 3 nitro groups, suppose you have 2, 4, 6 trinitro chlorobenzene, then the species simply react with water on warming can give you the Cl minus can be replaced by OH minus. Okay, so with the presence of electron withdrawing groups, the nucleophilic substitution reaction enhances at the hydrogen atom. Let us see with the examples. See, when we are taking the chlorobenzene, the Cl is replaced by OH at 623 Kelvin. Whereas when an electron withdrawing group NO2 is present here in the para position, now this Cl is replaced by OH at just 443 Kelvin. When we are attaching 2 nitro electron withdrawing groups to this benzene ring, then the hydrogen atom is replaced by the OH at just 368 Kelvin. And where 3 nitro groups are attached, then the hydrogen atom is easily replaced by the OH simply from water on warming. That means the presence of electron withdrawing group enhances the nucleophilic substitution on the halogen, and this enhancement increases with increasing number of electron withdrawing groups. So when the number of electron withdrawing groups are 3 here you simply the hydrogen atom is replaced by OH minus from water on warming. Whereas when we are not having any electron withdrawing groups, then the hydrogen atom requires 623 Kelvin to replace by OH. And this temperature decreases with increasing number of electron withdrawing groups. So this indicates how the reactivity of halogen is enhancing by the presence of electron withdrawing groups. Okay, simply here we are getting the phenol, here we are getting pan-nitrophenol, 2,4-dinitrophenol, and 2,4,6-dinitrophenol, or also this is called picric acid. Okay. Now action with the metals like haloalkanes, haloarenes also react with the active metals like sodium, magnesium in the same manner. Like haloalkanes react with the sodium metal in dry ether to give alkane called Wood reaction. Similarly, here also see the haloarene, this is your chlorobenzene react with the sodium metal, 2 molecules. In case of dry ether, give what your biphenyl or diphenyl. This is called what your Fittig reaction. This is called what your Fittig reaction. So 2 haloarene molecules react with sodium metal in dry ether to give what your biphenyl. So this is just write like a dry ether, okay, called Fittig reaction. Similarly, when a haloarene react with a haloalkane in case of dry ether with sodium metal, we are getting what is toluene. See, chlorobenzene react with your methyl chloride in dry ether to give what is toluene. So haloarene gives what biphenyl, but haloarene and haloalkane we are taking what this one N and alkene. Now similarly haloarenes react with the magnesium in dry ether to give what phenyl magnesium bromide known as Grignard's reagent. So bromobenzene react with magnesium metal in dry ether give what phenyl magnesium bromide known as Grignard's reagent. And this from this Grignard reagent we can prepare many other compounds. Now this is your iodobenzene react with the copper metal to give what diphenyl. Okay, so haloarenes react with your sodium metal, magnesium, and also copper. Okay, 2 molecules of haloarene, 2 molecules of chlorobenzene react with sodium metal to give it biphenyl in dry ether. Now 1 chlorobenzene, 1 methyl chloride react with sodium metal in case of dry ether gives your toluene. This is called Wood's Fittig reaction. And bromobenzene react with magnesium metal in dry ether gives the phenyl magnesium bromide called Grignard's reagent. And iodobenzene react with copper to give the diphenyl or biphenyl. So this is about what the chemical properties of haloarenes. Polyhalogen compounds, uses and their environmental effects. So these are the different polyhalogen compounds, uses and effects. Just we remember, if you take dichloromethyl, DCM called DCM, see this is your CH2Cl2. This can be used as a solvent and can cause damage of eye, burning, sensation to skin. If you take your trichloromethan CH3, also called chloroform, this can be used as a solvent and also it is used as a anesthetic. It is used as an anesthetic. This can cause damage to kidney and liver. Now this chloroform can produce a poisonous gas called phosgen when come in contact with the air. Chloroform come in contact with the air, this is called phosgen COCl2. Now another one, we can take carbon tetrachloride CCl4. This can be used as a fire extinguisher under the name pyrene. This can cause depression of ozone layer. Now benzene hexachloride BHC can be used as a pesticide. It is bio non-degradable and it is causes different environmental degradation and also it is a damage to crops. Now DDT called diphenyl trichloroether. Okay, this is also used as an insecticide and these are all harmful to humans. Then also freons are there. Freons are one example is chlorofluorocarbon freon 12. This is used as a refrigerator and this is harmful to environment, causes depression of ozone layer. Okay, so there are the different polyhalogen compounds, uses and compounds that we have to remember.